Okay. This is part of of lecture 5 that we didn't cover on Friday. I'm going to jump right into it here for time's sake. So as I told you in class, I'd like to address polar coordinates. They're not a huge part, but enough that I thought I'd make this short video about them and explain them and then do an example. And then be sure to look at my other videos that are going to be examples of chapter 12 material, F equals MA, so that you can best do the homework. As I said, you should be able to do with the material I provide, you should be able to get through the homework. Anyway, so this is, if we look at polar coordinates, and I'm going to draw this out, so I'm just going to show you this slide first. So this is the equation for velocity, and this is the equation for acceleration. Now, at first, it looks fairly complicated, but let's go through it. So first off, looking at this here, our polar coordinates are based on, of course, an origin point, and then we know the radius that goes to wherever, if our particle's moving in a curve, then that's the radius of curvature at that particular point. And then at that particular point, we can describe the radial position, which would be going in the continuation of the direction of r, and the theta, which we think of as the transverse direction as it's going normal to the direction of the r. Okay, so let's do this. So here we have, if we were to think about velocity on a curve, we would have VR here and V theta there. And of course, if we add the two together, then we get the total velocity direction it would be. And so that's just adding the two vectors VR. So V would be equal to V theta plus VR. And of course, we know that those are, again, being vectors, they are defined by V equals R dot, which we know is just the change in R with respect to time, times the unit vector ER. So that's just our unit vector direction in that. So that makes sense. It's just the first derivative of the change in position with time, and then the change of position with time with respect to R. And then we have R times theta dot, okay, times E theta. So we call this here radial velocity, and we call this transverse velocity. All right, so we have radial velocity, transverse velocity. All right, so then leads us to acceleration. Now, these can be derived fairly easily. I'm not going to show you the derivation. The derivation for acceleration takes about 45 minutes, and I don't really see a big advantage to doing the derivation since we're going to not use polar coordinates that much. But I think more importantly is understanding the different terms of the acceleration. So for example, when we break acceleration down, we have the overall acceleration. And remember that when we talked about acceleration in normal tangential, we had two terms. So here we have the first term, which is going to be r double dot minus r theta dot squared, and all that multiplied by the radial unit vector. All right. So this is essentially the linear acceleration. In the r direction. Okay. So linear acceleration in our direction. So that would be in this direction. How fast is it accelerating in that direction? Okay. And then we have this. Well, this should kind of look familiar. This is what we call centripetal. Centripetal. That's P-E-T-A-L. C-E-N-T-R-I-P-E-T-A-L. acceleration. And remember that it's the equivalent of the v squared over rho. It's not the exact same, but that's what it's referring to. So remember, the centripetal acceleration is the fact that as you go around the corner, you're always accelerating back toward the middle. So that's what that term is. And then we add to that the term in the tangential direction. So we have the radial and the tangential. So the tangential, that's going to be r theta double dot. Okay, and that's just the change in uh, tangential direction with respect to time and so the theta dot would be our tangential velocity, theta double dot would be our tangential acceleration. And so that then we would define as the linear acceleration in tangential direction. All right. And the last term is kind of weird. It's the Coriolis acceleration. And it's not really relevant to what we need in this class. There's a lot of really good videos explaining the Coriolis acceleration. It's what causes tornadoes, hurricanes, and why they spin different directions depending on whether you're north or south of the equator. So that's kind of outside the scope, but that's what that term is. And so a lot of information on Coriolis acceleration when it comes to weather. So Coriolis. All right. So there's hard to explain what that physically does. If you spin a rod around, it's kind of what makes the particle fly off the end, but that's not even really good unless you visualize it. So again, if you're interested in what Coriolis is, there's lots to explain that. So you don't really have to know, all the definitions of these to really use them in our context. Like I said, we're limited on what we're going to do with Coriolis. So, but I do want to do an example just to show you how we would apply this stuff. So if we go back to our video, I'm sorry, to our PowerPoint. So here this is just more information about position acceleration. Again, what I showed you just now is I would have done this in tandem with that. I wouldn't worry so much about it. It's pretty much the same thing I just showed you. So this is what I want to do, this example here. So here we have a rod OA rotating in a horizontal plane, and then we're given that theta equals t cubed radians. And then we're also told that collar B is sliding outward along OA so that R equals 100t squared. In both cases, t is in seconds. Determine the velocity and acceleration of the collar when t equals 1 second. Okay, so we have these two things going on. So let's look at the actual example. So here's actually the problem. And so let's first off, as before, we're going to write out our equations. So we know acceleration equals r double dot minus r theta dot squared all times er plus r theta double dot plus 2r dot theta dot times e theta. All right, so there's our equation there. So the next step is to plug in the values so that we can actually determine what these respective things are. And what do I mean by that? Now this printed as Q, but it should have been theta. So sorry about that. My printer didn't like it. But we know that if theta equals t cubed, Well, then theta dot is equal to 3t squared, and theta double dot is just 6t, okay? And then we're also told that same time column B rotates outward, so that R is 100t squared. So R equals 100t squared. So R dot is just equal to 200t, and R double dot is just equal to 200. So the level of complexity of these problems in the book is just the calculus. So we could have given you, much harder functions with sines and cosines and different differentials that are, a little more hairy to take the derivative of. But that's really more of a calculus problem than a dynamics problem. That's why I don't dig as deep into this topic, because I don't want to get bogged down in the math. Not that the math isn't good, but it's just we have other things to worry about. So now that we have those relationships there, then we can look at what we have. Well, we're given that t velocity acceleration when t equals 1 second. All right. So let's also put up the velocity equation, which we know is v equals r dot plus multiplied by its unit vector. So let's make a little more space for that. R dot times plus r theta dot e theta. Okay. So then, well, since we want to know velocity and acceleration at t equals 1, well, then there we have it. So do this. So what is v? Well, r dot is 200t. So what's that going to be? It's going to be 200, right, times 1, and that's my radial. And then that's going to be plus r theta dot. Well, what's that going to be? R is just 100 times 1, so that's going to be 100, but then times theta dot. Theta dot is 3t squared. Well, if it's t is 1, then that's just 3, so it's going to be multiplied by 3, and then we get e theta. So we do the complex math, and we get v equals 200 in the radial plus 300 in the tangential. And there we go. That's our velocity. So that's the thing, is that though we can do a lot more with the polar coordinates, it's just a limited part of the class just for time's sake. All right. So let's go ahead and look at the acceleration then. And using the same relationship as this, we can just plug in and solve for the acceleration. So again, you're just going to take what you have here and substituting in the different parts. So we know, for example, r double dot is 200, and r theta dot squared, so let's just, a is going to equal 200 minus 100 times 3 squared times er plus 100, right, going by that, times theta double dot, so that's 6, plus 2 times 200 times 3. Just plugging all this in. And that gives me e theta. So if I simplify this, I get my acceleration is equal to negative 700 plus 1800 e to the theta. And that's in millimeters per second squared. All right. So that's with the units that we're given. That's what we have. All right. So we can calculate the angle. And so if we look at the angle phi and take the inverse tangent of 1800 over 700, we get an angle of 68.7 degrees. Now, what does that mean? So if we look at, grab my ruler, let's draw this. So first off, let's put velocity on here. Now, one of the things you notice is that this theta, this is where we started from. So this was our initial point here, and then we moved 1 theta. So we know that if theta is 1, that means we moved 1 radian. Well, 1 radian is equal to 57.3 degrees. All right, so we know this is 57.3 degrees. If we were to plot the velocity, we'd get something like this. That would be our 300, and that would be our velocity in that direction, the tangential. And then if we looked at our velocity coming out this way, then we know that's 200. So our net velocity, if need be, would be something like that. And that would be 361 millimeters per second, sorry. And then we could calculate that angle as 56.3 degrees just using tangent for 300 and 200. So 56.3, sorry, it's hard to see. And then that's that. So, but then I'm going to erase that. So let me hold it up. So you have 57.3 is where we plotted it. And then this is 56.3. That's between the 300 and the 200 and the magnitude 361. All right. Now, if I erase that, so I don't have 2 of these. I want to plot the acceleration also. Now, so for the acceleration, you have acceleration radial going back toward, so we know there's an acceleration going in that direction, right? Because it's negative 700, so it's going toward it. We still have the 57.3, that hasn't changed. And then we have, so this is our AR, and this is our A theta here. So what we know now is that the magnitude is going to be 1930, and that's the magnitude of it, millimeters per second squared. And then if we look at the overall angle that goes all the way around to here, okay? So, you could go this way, you could go all the way around, but if we want to know what that angle, it's essentially 50, we'll say phi, and so phi is 57.3 plus 180 minus 68.7, okay? And so we get 169 degrees. So this whole angle, 169. Or you could take, that'd be like 11 degrees over here. So again, if you're trying to plot it on there, but the most importantly is that it's going backwards, it's going that way, and that's going that way. All right. And that's pretty much the extent of what I'm going to do with polar coordinates. So as long as you understand this equation, you should be in good shape. All right. So that's what I want to talk about on Friday, but of course we didn't have time. So I'll leave it at that. And now I want to move on to chapter 12 examples in the next videos. Thank you.